Okay, so now we're going to talk about theorem 2.1, which is the area of a region between two curves. All right, now if we have two functions, if we have a function f of x, like this one, f of x, and g of x like this one, so we have two functions f of x and g of x that are continuous on a closed interval from a to b. So we have f of x and g of x, and they're continuous on this closed interval from a to b. So notice between a and b, the g of x is continuous, no holes, gaps, or jumps, and f of x is also continuous, no holes, gaps, or jumps. So that's the setting. We have f of x and g of x being continuous functions on the interval ab, and also the g of x is less than or equal to the f of x for all x and y in AB. So basically that says that the g of x, this blue function, is below the f of x, this red function, for all the x values between a and b on the x-axis, which is true here. The red function is indeed above the blue function for all the values of x between a and b, including a and b. Actually, at a and b, they're equal to each other. Okay, so as long as you have two functions that fit that criteria, continuous functions on an interval from a to b, where f is bigger than g for the entire interval, then the area of the region bounded by the graphs of f and g, the area basically they're talking about is the area of this region in here. So they're talking about basically this area in here. Uh, if you want to find the area of this region in here, the area of the region I'm cross-hatching, that area of the region bounded by the graph of f and g is going to be calculated using this integral. So the area A, the area in here, A, that area can be found by calculating this interval. All right, and actually, it's actually talking about these vertical dashed lines A and B. We're going to see some problems like that also, but in general, you're going to have to find the interval AB on your own. So that's the theorem 2.1, the area of the region between two curves. Okay, so now we're going to look at an example of using this theorem. And the example we're going to look at, we're going to have f of x to be negative x squared uh, plus 4x plus 1, and we're going to have the g of x be x plus 1. So we have basically here a parabola and a line. Oops. And what we're going to do is we're going to identify all the parts of this theorem so we can plug um, all our numbers in. So uh, let's see. We have the f of x and g of x given to us, and both of these are polynomials, so they're definitely continuous on the entire real number line, so we don't have to worry about them being continuous on AB. Um, it says that we want f of x to be greater than or equal to g of x, or conversely, g of x to be less than or equal to f of x for all x on the interval from a to b. We don't have an interval from a to b, so what we have to do is we have to find out where these two graphs intersect. And in order to do that, what we have to do is we have to set the f of x equal to the g of x. That's the first step, to find out where these two graphs cross each other by setting them equal to each other, finding out where they have equal y values. What we're doing now is finding the x values where these two functions have equal y values. So let's go ahead and do that. We get negative x squared plus 4x plus 1 equaling x plus 1. That's the f of x equaling to the g of x. Now we're going to solve this equation. To solve it, we subtract x from both sides. Subtract x. we subtract 1 from both sides, subtract 1. And when we do that, we get a quadratic equation that equals 0. We get negative x squared um, plus 3x. These cancel out, so we get equal to 0. So we have this equation now, and in order to solve this, well, we can go ahead and factor. We can factor out actually a negative x. And if you factor out negative x, you're left with x minus 3 equaling 0. And you get 2 points where these graphs cross. You get x equals 0 for the first one. That's for this first factor. And you get x equals 3 for the second one. That's for this second factor here. So we get the two values, 0 and 3. So we have identified a is equal to 0, the smaller of the two numbers, and b is equal to 3. So um, what we need to know is we need to know which one of these functions is smaller and which one is larger on the interval from 0 to 3, that interval from a to b or 0 to 3. So what we're going to do is we're going to find out which one of these is larger on this interval. And on the interval from 0 to 3, what I'm going to do is I'm going to choose a number on that interval, and I am going to go ahead and uh, plug it into both functions to see which one gives us the larger value. The number I'm going to choose from this interval is the number 1. So 1 is a number between 0 and 3. So I'm going to plug that number in um, to both f and g to see which one is the larger value, because I need to know on the interval from 0 to 3 which one is larger, f or g. So let's go ahead and find the f of 1. Well, the f of 1 is going to equal negative 1 squared plus 4 times 1 plus 1. And if you do this arithmetic, you get the f of 1 is equal to 4. So the value of f on the interval from 0 to 3 is, or actually the value of f when x is equal to 1 is 4. Now let's find the g of 1. Well, the g of 1 is just going to equal 1 plus 1, which is 2. So it turns out on the interval from 0 to 3, the function f has larger y values than the function g does. So it turns out that this is indeed true, and f of x is bigger than or above g of x for the entire interval from 0 to 3, because these are the only two places where they equal each other. And so anything that happens between these two numbers happens for the entire interval, and anything that happens on the outside happens for those entire intervals. So we've found our a and b. We verified that the function f is above the function g for the entire interval from a to b, and now all that's left is to find the area. The area of the region bounded by the graph of f and g, and the vertical lines x equals a, which would be x equals 0, and x equals b, which would be x equals 3. The area between those curves is given by this. Area is equal to the integral from a to b, or from 0 to 3, of f of x minus g of x dx. So let's go ahead and calculate this area. All right, let's get rid of these calculations that we use to find a and b. And now we're going to find the area using this formula here. So it says that the area is equal to the integral from a to b, which is from 0 to 3, of the f of x minus the g of x dx. So let's do that. The f of x minus the g of x dx. Well, let's see. The f of x was negative x squared plus 4x plus 1. And we're going to subtract from that the g of x, which is x plus 1. And we're going to do the integral of that difference, with respect to x. So we get that the area is actually equal to the integral from 0 to 3 of, let's combine like terms here. We get negative x squared, and then 4x minus x is plus 3x, and then positive 1 minus 1 is 0, so what we're really integrating is this function with respect to x, in which case we get negative 1/3 x to the third plus 3/2 x squared, and we're going to evaluate this between 0 and 3. So now all that's left is to plug in the upper and lower limits of integration to find the area. So the area is equal to negative 1/3 times 3 to the third power plus 3/2 times 3 squared, and then from that we're going to subtract what we get when we plug in the lower limits, which is negative 1/3 times 0 cubed plus 3/2 times 0 squared. So this calculation will give us the area. Let's see what this equals. So let's see. This first term would equal negative 9. The second term would equal 27/2. And those last two terms would just go to 0 because they're products that involve 0. Okay, upon addition here, we get the answer to be 9/2. So what we found out is that the area of the region bounded by f of x and g of x is equal to 4.5, and that would be the answer for the area of the region bounded by f and g.